Okay. And so trying to develop some numerical methods for understanding fracture, we'll consider how in the ductile failure mode, how fracture develops, and look at ultimately stress concentration. So what we'll consider here is just how in the moment where we have post-nucleation and coalescence of voids to generate our crack, that stress sigma, stress ends up concentrated and focused at the limits of our crack. So that is at the sort of head and the tail of our crack. So note here the force lines sort of showing how the stress is taken through the material in our tensile condition here. How all those stress lines end up focused at the ends, given that there's no matter in the crack, and so we can't propagate stress through a void in the middle of our crack. Okay, so like Da Vinci had noticed, flaws in the material are detrimental to the fracture strength of the material. And so clearly flaws like internal voids or internal particles or even surface flaws are going to focus stress at the head of these cracks. So let's use that idea to build up our model for this. So what's applied here typically as an elliptical shape is used to represent the shape of the surface flaw. So here we would apply an ellipse to represent a surface flaw. Or, of course, we would represent an internal crack with an ellipse as well. The parameter characterizing the ellipse is twofold. There are a length to the surface crack. Okay, so that would be A. You can see here it's how deep that sort of ellipsoidal model representing the surface crack is. Okay, so here you can see the A value for a surface defect or surface flaw. If the flaw or the crack is internalized, then we apply 2A. So that is a full ellipse here of length 2A is used versus a model that uses a half ellipse. Half ellipse to represent the surface flaw. Okay, so that distinguishes the sort of 2A for the full length of the internal crack versus a surface version that's only A in overall depth. The second parameter we need is the radius of curvature. This characterizes how sharp this feature is. How sharp is this crack? And so there, a sphere is applied, and the radius of this sphere, which represents the contour, the sharpness of our ellipse, is what's used, and the radius value here, given rho sub t, is the second parameter for characterizing this crack, either internalized or at the surface. So that same spherical model is applied at a surface flaw, again represented by a half ellipse. We see those two parameters built into our stress equation. Okay. So the stress at a crack tip is sigma m. The stress at a crack tip is a function of these ellipsoidal parameters represented here by the fraction raised to the power half. So we have the depth of the surface crack, or the half length of the internal elliptical crack, divided through by the radius of curvature of that ellipse. Okay, so that piece is just sort of geometric, if you want. Outside of and ahead of that is a coefficient that is simply the applied tensile stress, sigma naught, and that is doubled. Okay, so 2 sigma naught times the geometric parameters for the ellipse characterizing the sort of length of it, either on the surface or internalized, divided through by its radius or curvature, all to the power of a half, is how we calculate the stress at the tip of a crack. So you can see here that sigma m, the stress at the tip of a crack, is always going to be larger than sigma naught, given the presence of surface flaws or internal flaws, like an ellipsoidal crack or an half ellipsoidal surface flaw. Okay, so for this reason, materials will fail well below what we expect based on overall stress applied, because there is stress concentration at these flaws. Okay, so given that, let's just clean that up. And advance our slide. We can see here how sigma m builds as we get closer and closer to that internal surface crack. Okay, so imagine a crack that is along the length of x to x prime. And so here you can see its location in the middle of our graph. And so here we're monitoring stress. So when we're very, very far away from that crack, the stress on the material, green, is approximately equal to the stress applied, sigma naught. As we get closer and closer to that surface and tip of the crack, we can see that actual applied sigma is building towards the ultimate sigma m value, which we can predict from our equation. So once we reach and get close enough all the way to our tip of our crack, you can see that we reach the limits predicted by our equation, sigma m, and everything in between is a higher stress value than that applied on the bulk object. So this is the term and the concept of raising stress or stress concentration. Okay, so this shows the amplification of stress. It shows that it's more significant in brittle materials than ductile materials. And we'll see that's the stress concentration factor, ultimately the sigma m predicted from the above divided through by the applied stress on the whole object, is kT. That is our stress concentration factor. So if stress concentration factors are very, very high, we have a very sharp internal crack or surface flaw to give a large sigma m value as an example. Okay, so this is characterizing the degree to which the external stress gets amplified. That's the K sub T value. Okay. How about in brittle materials? So in brittle materials, we have similar ideas. In this case, the critical stress to propagate a crack in that brittle material is going to be derived from a similar geometric feature representing the depth or distance of the internal crack, should it exist in the ceramic material. So there we have A again, okay? So 1/2 of the length of the internal crack, or if it's present on the surface, the full length of it. Our denominator in this time has pi in it, and our numerator has now the elastic modulus as well as the specific surface energy of the material. Okay, so here the specific energy of the material is the energy of the material normalized for the cross-sectional area. So typically joules per meter squared are units there. And recall we've seen pascals or gigapascals for our modulus values there. And of course, A would be measured in distance of meters, for example. Okay, so similar ideas here. We again use an ellipsoidal model to represent a feature on the surface of a brittle material, and now the critical stress to propagate a crack is given by this equation. Okay, very good. So let's take a look at an example here in brittle materials. Let's look at this question. It says, calculate the maximum allowed length in micrometers of a surface flaw on a large plate of glass. Okay, so this is our hint. Glass is a ceramic material, so I'm allowed to use my brittle materials equation. And we want to allow the largest surface flaw such that it will not fracture under tensile stress of this value. So this is typical of materials challenge, where we know ultimate load or stress to be applied to a piece of glass, and of course we do not want it to fail or break or propagate that crack. We're given the surface energy of this glass, so it is 0.3 joules per meter squared. So recall that this is gamma S, the surface energy. And we're also given the modulus of elasticity of the glass. So this is going to be a very high value, very steep stress strain curve. So this is going to be 69 gigapascals for E. Okay. And we're also told that, as a hint, that 1 joule is equal to 1 Newton meter. Okay, sort of like the work equals force times distance equation is hinting at that. Okay, so take a minute, see if you can use our equation down below and the given information, and see if you can determine the maximum allowed length of a surface flaw that that is allowed and will not fail. Okay, so after you've had a chance to do that, resume the video and we'll take a look at this. Okay, so we saw that sigma sub c, the stress to propagate a crack in a brittle material, was equal to 2 times the modulus times the surface energy, all divided through by pi times the length of that surface feature. And this was raised to the power of a half. And so we are asking about the ultimate length of the surface feature. So what we want to do is solve for A. Okay, so doing that, we'll take the square of both sides. Pi A. We'll then maybe move the numerator to the other side, so we'll end up with pi A is equal to 2e gamma S divided by sigma c squared. And ultimately we see here that A is equal to 2e gamma S divided by pi sigma c squared. Very good. Okay, so we were told earlier that the value for E was 69 gigapascals. Okay, so E is equal to 69 gigapascals. And we were also told that we had 0.3 joules per meter as the sigma S. Joules per meter squared. And we were given a hint that 1 joule is equal to a Newton meter. So let's see what happens if we put in the Newton meters here. So 0.3 Newton meters divided by meters squared. Alternative unit for that surface energy is 0.3 newtons per meter. Okay, and finally we have the stress to be applied. So this represents the stress limit, sigma C. Okay, so sigma C was 25 megapascals. Okay. So in order to cancel units properly, as we know, a pascal is simply a Newton per meter squared, it would be to our benefit to get out of these units. So we're going to go into simply pascals or newtons per meter squared. And we'll have this instead reflected as 25 times 10 to the 6 newtons per meter squared instead, which is of course a pascal. Likewise, on our modulus, this is 69 times 10 to the 9 newtons per meter squared. And of course, a newton per meter squared is a pascal. So with those, I think we can populate our equation and see how units will cancel. So 2 times the modulus value in pascals, or newton per meter squared, is now 69 times 10 to the 9 newtons per meter squared, times the surface energy value, which we've transformed into newtons per meter, 0.3 newtons per meter. And all this has to be divided through by pi times the sigma C value, 25 times 10 to the 6 newtons per meter squared. And let's just take a look how units are going to cancel on this one. Okay, so oh, I'm sorry, we forgot the square up here. Okay, notice the square there. So newtons times newtons will be newtons squared, and that newton squared will disappear therefore. We will end up also with per meter cubed in the numerator, and we're going to cancel 2 of them. So the numerator is going to be in our denominator is going to be per meter to the 4. So that'll end up leaving us with simply meters behind. Okay, so notice meter 2, meter 1, so that's meter 3, and then we're going to be meter 4. So we'll end up with just meters that way, which is the right units for a length feature of A. Okay, so after doing this, you should get something like 2.1084 times 10 to the minus 5 meters, or if we had to go into a sort of unit more representative of typical flaws, go into micrometers. This would of course be 21 micrometers. Okay, so 21 micrometers is about the width of half a human hair or so. And so this lets you know that a flaw that would be 21 micrometers in surface depth on our piece of glass, if this were 21 micrometers deep, that our material would fail under the condition of 25 megapascals. Okay, so our surface flaws must be lower than 21 micrometers if we're to not propagate a crack in this brittle material.